fast algorithm for complex NMF with application to source separation. What is NMF? You are given a matrix M. The goal is to find W and H such that M is equal to W times H. For more about NMF, you can refer to this book. So NMF is a model on real numbers. How do we extend it to a complex number? We can introduce the phase. For a complex number, we have polar expression. R is the amplitude, EI theta is the phase. So for this complex matrix M, we can introduce amplitude part, the phase part. This theta is real, but this whole part is complex. With this CNMF, we actually have three models. First of all, this kind of extension from real NMF to complex NMF has already been studied in the literature, but we call it rank 1 one phase because this WH can be expressed as R rank 1 component, and all these components are sharing the same phase. So we name this model one phase. To generalize this model, we just assume that each rank 1 amplitude part has its own phase. In this case, we have the rank 1 multi-phase model. In general, we further relax this rank 1 restriction to a rank Rj restriction. It means that a group of rank 1 components all together, they contribute to the source amplitude spectrogram. So in this case, we have this grouped multi-phase model. Notice that model 1c subsume model 1b, which subsume model 1a, which subsume NMF. Therefore, studying how to solve model 1c is important. CNF model has this form. We are minimizing a cost function plus a regularized term. We are not going to talk about too much about this R. Please refer to the paper. So how do we solve this problem? Rectangle calculus. The key point is that the W calculus works on the stacked vector of Z and the Z complex conjugate, not Z. For this coordinate, the derivatives are defined as follows. And with this definition, we can define gradient as follows. And lastly, point 4 means that for this function f is real valued, we only need to compute one part of this long partial gradient. So how do we exactly solve the CNF problem? We have three variables, W, H, and theta. So we perform alternating update. And what's the update? In principle, you can do whatever update you want, but for simplicity, let's consider projected gradient descent. That is, for a variable x, the new variable is obtained by performing the gradient step. After that, you perform a projection to the constraint set. Alpha means step size. For the theory of a gradient descent, this alpha has to be smaller than 2 over L, where L is the lift shift constant of this gradient. So for our CNMF problem, this is the objective function. We need to compute the gradient with respect to W, H, and theta. And since we are working on W calculus, we need to compute the gradient with respect to W Hermitian. And we show that in the paper, this is the expression of the gradient. We also show that this expression is this lift shift. So everything looks nice, but in fact, we have no convergence guarantee for this algorithm. Notice that classical theory of alternating update, they work on Rn to R. But here, the problem is Cn to R. So it is not clear whether this theory on this real vector n can be applied to our case. Even though if this can be applied to our case, the algorithm convergence is still not clear because the projection on theta is non-convex. Please refer to the paper for the detail. And because the algorithm, we do not have a theoretical convergence, so we propose to make use of numerical acceleration called HER. This method is proposed by me, and we show that this method is super effective on a bunch of factorization problems such as NMF, NTF, CPD, and more. For details, please refer to this paper or these papers. We apply this HER scheme on these CNMF models, and we found that it's very good. How good? We are running the free CNF model on free real audio data. Here, this figure shows the algorithm 1, that is the alternating update of WH theta. So this is the convergence. And then this red curves shows the algorithm with the HER extrapolation, and you can see it improved much better. And here, this is data on voice. You can see that for the convergence, after 1000 iterations, the convergence of the unaccelerated method is about 100 times bigger than the red method for just about 20 iterations. This kind of crazy acceleration is even more significant for the group CNMF model. And we can see that for just about 10 iterations or about a few iterations, the extrapolated method already goes to the convergence. Summary: general complex NMF model that subsumes two classes of CNMF and NMF, and very fast algorithm for solving this CNF. For details, please refer to these papers. The method of the extrapolation are presented on these papers. If you are interested, you can look for the first one and also the last one.